Welcome aboard, traveller. You've just stepped onto a strange little spacecraft. It doesn't look like much. No flashing lights, no noisy thrusters. Just a quiet voice and a few billion numbers, drifting gently through space. This is the sleepless mathematician. And tonight, we're going on a journey where math meets madness. Where a tiny mistake, so small it could hide behind a decimal point, quietly destroyed a $327 million spacecraft. Yep, you heard me. 327 million. Gone. Just like that. Poof, because someone forgot to check the math. And no, this isn't fiction. This isn't one of those made-up bedtime stories where dragons solve equations. This actually happened to NASA. In real life. On Earth. Well, sort of. It started on Earth. Ended somewhere near Mars. But don't worry, you're not in danger. The only thing that might crash tonight is your consciousness. Slowly, peacefully, as we sink deeper into this absurd, wonderful tale of numbers, humans, and a tragic little typo in the void. So, here's what's going to happen. I'm going to talk about math, but not the kind your high school teacher threw at you with a dead stare and a whiteboard marker. No, this is cozy math, story math, funny math, math that went very, very wrong, math that teaches us things we never thought we'd care about. And while I'm talking, your brain will start to drift. Maybe you'll laugh once or twice. Maybe you'll suddenly realize halfway through a joke about Isaac Newton that you missed 5 minutes of this video because you were already half asleep. That's perfect. That's the goal. Because this isn't just a story, it's a lullaby. A gentle one, wrapped in logic, laced with mistakes, and carried on the soft shoulders of arithmetic. Still with me? Good. Let's set the scene. The year is 1999. The world is nervous about Y2K boy bands are still a thing, and NASA, the mighty space agency, is preparing for a mission to Mars. It's called the Mars Climate Orbiter. Sounds fancy, right? And it was. This beautiful hunk of hardware was supposed to orbit the red planet and study its weather, take photos, analyze the atmosphere, help us understand Mars, so that eventually we could send people there without melting them in a sandstorm. Everything was going according to plan. The orbiter launched from Earth. It soared into the sky with that classic NASA confidence. Mathematicians, engineers, and scientists all held their breath. And then, silent. Just before the spacecraft was supposed to enter orbit around Mars, it vanished. No signal, no data, nothing. It was just gone. Like that one sock in the dryer. Only the sock cost more than most small countries. Now, you might be wondering, did it explode? Get hit by an asteroid? Sucked into a wormhole? Abducted by Martians? Nope. None of the above. What happened was math. A unit conversion error. One team used imperial units. The other used metric. And somehow, no one noticed. So when the spacecraft tried to enter Mars orbit, it came in way too low, like scraping the top of the atmosphere low. It burned up, or bounced off, or both. No one's exactly sure. All we know is, it never came back. And that's the story we're about to explore. Piece by piece, like a detective slowly unfolding a napkin that has the clues to a cosmic crime. But don't worry, this won't be a cold case. Because along the way we're going to talk about some wild stuff. How math literally flies spaceships. How Isaac Newton accidentally became a space influencer. Why Americans still refuse to switch to the metric system. And how that stubbornness might have cost them a spaceship. We'll talk about other math disasters too, like bridges that fell down, planes that crashed, stock markets that broke, all because of a little math misstep. We'll even talk about love. Yep, romance. Because believe it or not, math shows up there too. Ratios, probabilities, statistical models of dating success. Love is basically algebra with better marketing. And we're going to do all of this in the most relaxing way possible. No rushing, no heavy calculations, no shouting. Just slow, dreamy math talk. Now, in case you're not familiar with my style, let me reassure you, you won't need a calculator, or a degree, or even a brain that's fully awake. You can just sit back, listen, and let the numbers float by like little stars out your spaceship window. Math doesn't have to be scary. It doesn't have to be dry. It can be strange, funny, beautiful, even soothing, especially when you realize that it's everywhere, in every breath, every step, every broken Mars orbit. And if all goes well, you'll be asleep long before I get to the part where we explain what a pound-for-second is. But if you're still awake by then, don't worry, I'll explain it. Gently. I promise not to whisper equations into your ear like a cursed math ghost. So, are you ready? Take a breath. Let it go. Picture this. You're working at NASA. You wear khakis, maybe a short-sleeved button-up. Your coffee is half cold. You've barely slept in weeks. But today's the big day. The Mars Climate Orbiter is about to enter orbit around the red planet. You've worked on this thing for years. Thousands of people have. Engineers, programmers, mathematicians. The mission has cost over $300 million. That's roughly one very fancy yacht per bolt. Everyone's tense. Eyes are on the screens. Beeps. Data. Code streaming in green letters like something out of the Matrix. Except this is real life. This is space. And then, nothing. Just silent. No signal. No beep. No happy message saying, "Hey, I made it to Mars." Just a cold, empty gap in the data feed. The spacecraft was there, and now it's not. It was September 23rd, 1999. That's the day the Mars Climate Orbiter disappeared forever, and no one knew why. At first, they hoped it was a glitch. Maybe the signal was delayed. Maybe it was hiding behind Mars. Spacecraft do that sometimes, like a kid playing hide-and-seek behind a planetary rock. But as the minutes passed, and then hours, it became clear the spacecraft wasn't hiding. It was gone, vanished, lost in the cold, unforgiving vacuum between planets. What happened? That's what everyone asked. And the answer is so beautifully ridiculous, it belongs in a bedtime story, or a sitcom, or both. It wasn't sabotage, not a computer virus, not a Martian laser beam. It was a math error, a simple one, a mistake so basic it should have been caught by a sleepy intern on a Monday morning. Here's what happened. Two teams were working on the mission. One team was responsible for writing the software that calculated the spacecraft's thrust, how much force the engines produced during little course corrections. The other team used that information to figure out where the spacecraft was and where it was headed. Sounds simple, right? Just some numbers, some math. Input, output, job done. Except they weren't using the same units. The software team, working with Lockheed Martin, used imperial units. Pounds, feet, slugs, all that good old American stuff. Meanwhile, the navigation team at NASA was using metric units. Newtons, meters, kilograms. You know, the system used by almost every other country on Earth, and the entire scientific community. And astronauts. And literally every textbook since So what happens when you think you're getting data in newtons, but you're actually getting it in pounds? Disaster. That's what happens. The spacecraft, guided by wrong calculations, entered the Martian atmosphere way too low. Instead of gliding smoothly into orbit, it skimmed the atmosphere like a flat stone skipping across water, except the water is made of carbon dioxide and fire. The best guess is that it either burned up instantly or bounced off and tumbled into deep space, forever drifting like a very expensive paper airplane. Let's take a moment to appreciate this. This wasn't a coding bug. It wasn't a structural failure. No one forgot to bolt a panel on. It was a math error, a unit mismatch, like confusing teaspoons with gallons. But instead of ruining dinner, it ruined a mission to Mars. It's the space equivalent of ordering coffee in milliliters and getting it in gallons. And by the time you realize it, you've drowned in caffeine. But wait, how did this happen? Doesn't NASA triple check everything? Yes, usually. NASA is famous for being meticulous. They're the kind of people who label their labels, who double check the double checks. But sometimes when teams are split, communication breaks down, assumptions are made. Everyone thinks someone else is checking the details. And that's the thing about details. They matter, especially in space, where there's no margin for error, where being off by 1 degree means missing a planet by 1,000 kilometers. After the incident, NASA launched an internal investigation, and what they found was embarrassing. The problem wasn't complex. It wasn't hidden. It was right there in the data logs. The software reported thrust in pound force seconds. The navigation team read it as Newton seconds. And nobody converted. 1 Newton is about 0.2248 pound force. So if you're reading pound force numbers thinking they're newtons, you're off by a factor of about 4.5. That's like trying to bake cookies at 2,000 degrees instead of 450. The results are suboptimal. This tiny mismatch led to incorrect calculations, which led to incorrect trajectories, which led to a spacecraft entering the Martian atmosphere like a bowling ball falling off a skyscraper. There were no astronauts aboard, thankfully. No one died, just a lot of red faces, a lot of lost money, and one very sad little spacecraft. NASA officials described it, diplomatically, as a navigation mishap. That's like calling the Titanic incident a buoyancy discrepancy. But in the grand scheme of things, this mission failure became a legend, a cautionary tale, a math teacher's dream, proof that units matter, that precision matters, that even the smartest people on Earth can make dumb mistakes if they stop asking questions. And that's the beauty of this story. It reminds us that math isn't just numbers on a board. It's not just tests and calculators and bored teenagers staring out the window. Math is power. Math is motion. Math is the reason a hunk of metal doesn't become space toast at 17,000 miles per hour. It also reminds us that math is fragile. One wrong assumption, one skipped conversion, and things fall apart. So the next time someone says, "Why do I need to learn math?" I'll never use this in real life. Just tell them this story. Tell them about the time NASA lost a spaceship because someone forgot to convert pounds to newtons. And then tell them to double-check their recipes, especially if they involve rocket fuel. Coming up next, in Chapter 3, we'll meet the real villain of this story, unit conversion itself. A slippery little beast that has ruined more than one mission, more than one bridge, and probably more than one marriage. But for now, just breathe, let the numbers drift.
Mars is still out there. So is the orbiter. Somewhere.
And we're just getting started. So, we know the Mars Climate Orbiter went out in a blaze of invisible glory, all because 2 teams couldn't agree on what a number actually meant. But now, it's time to meet the true villain of our tale. No, not an evil genius. Not a rogue engineer with a calculator and a grudge. No dramatic music necessary. The villain was unit conversion. That's right. Good old-fashioned, how many of this equals how many of that. The kind of thing you thought you'd never need after middle school. The kind of thing you Google when you're trying to cook an American recipe in a European kitchen. Now, don't let the name fool you. Unit conversion sounds innocent, even helpful, like a librarian who whispers gently, 2 cups is about 0.47 litres. But in reality, it's sneaky, deceptive, and capable of sabotaging multi-million-dollar space missions without making a sound. Let's back up for a second. What actually is a unit? A unit is just how we measure stuff. Meters, inches, litres, gallons, newtons, pounds, bananas, parsecs. Okay, maybe not bananas, but the idea is we use units to give numbers meaning. Saying something weighs 12 means nothing. Is it 12 pounds? 12 tons? 12 kittens stacked in a trench coat? Without the unit, the number is a mystery. Now, most of the world uses the metric system. It's clean, consistent, and based on powers of 10. It was invented in France during the Enlightenment when people were feeling bold and mathy and ready to overthrow kings and measuring systems. In metric, everything fits together nicely. 1 litre is 1,000 millilitres. 1 kilogram is 1,000 grams. 1 kilometre is 1,000 metres. It's like math with training wheels. And then there's the imperial system, also known as whatever the British were doing in the 1700s and forgot to stop. In this system, 1 foot is 12 inches, 1 yard is 3 feet. There are 16 ounces in a pound and 2,000 pounds in a ton. A cup is 8 fluid ounces, unless you're using a coffee mug, in which case, who knows, it's chaos. Beautiful, stubborn chaos. To make it worse, the US still uses it. Despite countless attempts to switch over, despite decades of scientists gently begging the government, please, please, let us join the rest of the world. Nope. America said, nah, we like our freedom and our Fahrenheit. And so, here we are, 2 systems, 1 planet, constant confusion. And in 1999, that confusion reached Mars. Let's get specific. The Mars Climate Orbiter's navigation depended on knowing exactly how much thrust the spacecraft was producing during each course correction. That thrust was measured in a unit called Newton seconds. Sounds cool, right? Like a secret math weapon. But really, it just measures impulse. The push a rocket gives over time. But the software team, working in Imperial, provided that data in pound-force seconds. They assumed the navigation team would convert it. The navigation team assumed the numbers were already converted, and everyone assumed someone else was double-checking. Spoiler alert, they weren't. Here's how off the numbers were. 1 pound force equals about 4.448 newtons. So if you use pound force when you think you're using newtons, you're making an error of over 4 times. That's like saying you're sending a gentle push and actually throwing a punch. Imagine trying to park a car, but every time you tap the brakes, the car rockets forward like it's being chased by angry bees. That's what happened to the spacecraft. It got pushed way too hard, way too low, and Mars just said, nope, and swatted it out of the sky. Let's pause here and just admire how dumb this is. This wasn't an engineering failure. The spacecraft itself was fine. The math formulas were fine. The physics was beautiful. It was just the wrong kind of number. It's like trying to bake a cake with the right ingredients. But you read tablespoons as cups, and suddenly your cookies are soup. You'd think there would be a universal rule in science. Always check the units. And to be fair, there is. But even the best of us forget, especially under pressure, especially when you assume everyone else is on the same page. But they weren't even in the same book. One team was measuring in inches, the other in centimeters, and nobody noticed until the spacecraft turned into an expensive shooting star. And here's the wild part. This isn't even the only time unit confusion caused chaos. There was an incident with Air Canada in 1983. A plane was misfueled because someone used pounds instead of kilograms. They ran out of gas mid-air. The pilots had to glide the plane to safety. They called it the Gimli glider. There was a bridge in Connecticut built several inches too short because of a metric to imperial misreading. They had to redo the road. There were medical dosing errors, space errors, military misfires, all because of this quiet villain. The unit conversion. It's a reminder that precision matters, and language matters, even in math. Because math isn't just about numbers, it's about what those numbers mean. If I say I have 12, that's fine. But if I say I have 12 nuclear warheads, suddenly the situation changes. Same number, very different meaning. So here's a gentle piece of wisdom from tonight's episode. Whether you're baking bread, flying a plane, or launching a spacecraft to another planet, always double check your units. Every time. Even if you're 99% sure. especially if you're 99% sure, because math doesn't care if you're tired or under pressure or very, very smart. If you feed math the wrong input, it will spit out the wrong result every time, quietly, without warning, like a very polite robot walking off a cliff. So now we know our villain. It's not evil, just sneaky, like a banana peel on the floor of a rocket lab. And we're not done yet. In the next chapter, we're going to talk about how math actually runs a spacecraft, how tiny equations control giant machines, and how, ironically, the thing that destroyed the orbiter was also what made it fly. But for now, rest easy. Let the numbers swirl around you. And try not to dream about converting slugs into newtons. Let's take a deep breath. We've yelled at unit conversions. We've watched a multi-million-dollar spacecraft vanish into the Martian atmosphere. It's been emotional. Now, let's zoom out. Float a little, because tonight we're going to look at how math, just plain humble math, is the thing that actually flies a spaceship. Not fuel, not buttons, not duct tape, just... Let's start here. If you ever find yourself floating in space, which I hope you don't, and you see a spaceship soaring past you like a cosmic jelly bean, that thing isn't just coasting, it's doing math. Constantly, every second, like a floating calculator, with really expensive solar panels. See, flying a spacecraft isn't just about going forward. Space isn't a highway. There are no lanes, no street signs, no GPS voice saying in 2 million kilometers, turn left at Mars. Space is just space. Endless, empty, silent, which means everything has to be calculated. Let's say you want to go to Mars. Easy, right? Just point and shoot. Wrong.
You can't just aim at where Mars is. You have to aim at where Mars will be, because both Earth and Mars are moving, constantly, around the sun, at thousands of kilometers per hour.
It's like trying to hit a moving target while you're also moving in a wind tunnel, blindfolded, with a Nerf gun. So, how do we hit it?
Math.
We calculate the orbits, the speeds, the distances, the acceleration due to gravity, the resistance or lack of it in space. We calculate how much fuel is needed, how heavy the spacecraft is, how fast it needs to go to escape Earth's gravity, then how to slow it down to not explode when it gets to Mars. All of this, every trajectory, every angle, every decision, is math. Let's take fuel, for example. In space travel, we use something called the rocket equation. It was invented by a guy named Konstantin Tsiolkovsky, who was basically the space version of your quiet math teacher, with brilliant ideas and zero friends. His equation tells us how fast a rocket can go depending on how much fuel it has and how efficiently it burns it. The twist, the more fuel you carry, the heavier the rocket. And the heavier it is, the more fuel you need to carry the fuel. It's like trying to carry a bag that keeps filling itself with more bags. So engineers have to calculate the perfect balance. Too much fuel and you're too heavy. Too little fuel and you just float sadly forever, waving at Mars as it disappears into the void. Math also handles course corrections. Spacecraft don't fly in straight lines. They curve, they drift, they wobble, gravity pulls them, heat expands them. Even sunlight can push them slightly off course. So engineers have to constantly adjust the path, just a little nudge here and there. Each nudge is called a delta V, short for change in velocity. And every delta V is based on a calculation, sometimes multiple calculations, sometimes hundreds. You can't just guess. Guessing in space is how you end up being the subject of a tragic documentary narrated by Morgan Freeman. Now let's talk about orientation, the spacecraft's attitude. No, not its emotional attitude. Its angle, which way it's facing. If the spacecraft is even a few degrees off, it might miss a signal from Earth, or burn up in the wrong direction, or try to land upside down. That would be awkward. So the spacecraft is constantly checking its attitude. using gyroscopes, star trackers, and math. Lots of math. And all of this is automated. The spacecraft isn't calling home every 5 seconds like a nervous teenager. It has to make decisions on its own, using algorithms built by people who haven't slept properly since the Clinton administration. These algorithms are written in code, and that code is based on math, functions, equations. If this then that logic. The kind of stuff you learn in algebra and wonder, when will I ever use this? Well, space. That's where even the simplest command, like turn 10 degrees to the left, has to go through a mathematical process. How fast to turn? For how long? What's the new orientation? Will that affect temperature? Will the solar panels still face the sun? Will the antenna still point at Earth? You can't just tell a spacecraft do a little spin. That's how you get space salsa. And of course, there's timing. Everything in space is about timing. When to launch, when to fire the engine, when to deploy the parachute. If you're even a second late, you could be miles off target. Mars doesn't wait. Neither does gravity. Neither does orbital mechanics. So NASA uses clocks that are accurate to fractions of a second, and every number is calculated down to the tiniest decimal, because a single digit out of place could mean the difference between landing on Mars or becoming a very expensive piece of space litter. And just to drive this home, let's not forget, the Mars Climate Orbiter was lost because of math, or more accurately, because the wrong math was used. All that beautiful calculation, all those perfect trajectories, all the brilliant algorithms, they were fed the wrong units. And math, being math, didn't argue. It just said okay, and did what it was told. That's the thing. Math doesn't care. It doesn't care if you're a genius or a beginner. It doesn't care if the project cost $300 million. If you give math the wrong inputs, you get the wrong outputs. Every single time. Like a vending machine that gives you tuna when you press chocolate. You can't blame the vending machine. You pressed the wrong button. It just followed instructions. So, the next time you think math is just something that lives in textbooks, remember this. It also lives in rockets, in orbits, in quiet spacecraft, drifting through space, silently solving equations that keep them alive. And in a weird way, that's kind of beautiful. Math doesn't need applause. It doesn't need credit. It just wants to work. Quietly, constantly, unseen, until someone forgets to convert pounds into newtons, and it gets blamed for crashing into Mars. Coming up next, we'll dive into some of the most expensive math mistakes in history. Spoiler, the orbiter wasn't the only one, but for now, let the spacecraft drift in your mind. Calm, balanced, quietly calculating in the dark. Let's start with a simple question. Have you ever made a mistake that cost you money? Maybe you forgot to cancel a subscription, or bought something online at 3 AM because it looked fun, and now you own a $20 inflatable moose. We've all been there, but unless you're hiding a secret NASA badge in your sock drawer, I'm willing to bet your mistake didn't cost $327 million. Because that's what the Mars Climate Orbiter cost when it became space dust. It's up there, floating somewhere in the Hall of Fame of very expensive whoopsies. And it got there not because something broke or exploded, but because of a simple math misunderstanding.
Now, let's be fair, NASA isn't the only place where a little error has led to a giant price tag. The world is actually full of math mistakes that cost so much money, they make you want to hold your calculator and whisper, "Please don't betray me."
So let's take a break from space, and take a calm little tour through some of the most expensive oops moments in human history. Let's start with a building. In 1995, the developers of a 47-story skyscraper in South Korea were feeling proud. The building was finished. It was shiny. It had shops and offices and escalators and everything you'd want in a fancy tower. Except one thing. It wasn't built properly. Due to a calculation error in the design, the building didn't have enough support columns. Engineers miscalculated how much load the floors could take. And one summer afternoon, The whole thing collapsed. Just like that. Killed over 500 people. The engineers had simply underestimated the weight of everything. All because the math was off. Next up, the stock market. In 2012, a trading firm in the US named Knight Capital was running some fancy software to help automate trades. This software relied on high-speed algorithms, basically math in overdrive, but someone forgot to remove some old code. Just left it in there, like forgetting to take out the battery before cleaning your toaster. And in just 45 minutes, the company lost $440 million. Not because of market crashes, not because of evil billionaires, just a math bug, a missing line of code. The firm collapsed. Game over. Now, let's jump to construction again. There's a bridge in Canada called the Quebec Bridge. Or, more accurately, there was a bridge. In the early 1900s, engineers were building the longest cantilever bridge in the world. It was ambitious, bold, beautiful, and totally miscalculated. The steel was too heavy. The math said it would hold. The bridge said, no thanks, and collapsed into the river, killing dozens of workers. They rebuilt it, and then it collapsed again. It eventually got built properly, but only after decades of redesigns and hopefully better calculators. And of course, we can't forget aviation. In 1983, an Air Canada flight was supposed to be fueled for a trip across the country. The ground crew did the math. But here's the twist. They used pounds instead of kilograms, so the plane had half the fuel it needed. Mid-flight, the engines shut down. Complete loss of power. Nothing. Just a glider full of very confused passengers and probably one pilot silently screaming inside his own head. Miraculously, they managed to glide the plane to an old airstrip and land safely. No one died. But that incident, caused entirely by a unit conversion error. Sound familiar? It should, because it's the same sneaky mistake that brought down the Mars Climate Orbiter. Now, here's a fun twist. Let's go back to the orbiter for a second. The total cost of the mission was around $327 million, and the cost of fixing the math mistake, if it had been caught, would have been maybe a few hours of someone's time, a line of code, a double check. Imagine walking past a piece of chewing gum on the sidewalk, ignoring it, and then slipping on it a week later and falling into a volcano. That's the level of avoidable we're dealing with here. But mistakes like this happen all the time. Why? Because humans are humans. We're brilliant, yes, but also forgetful, overconfident, busy, tired. We rush. We assume. We say things like, close enough, or that should be fine. And math doesn't care. Math will take your close enough and quietly build you a leaning tower of Pisa with it. Let's go back to our spacecraft. The Mars Climate Orbiter failed because of a misunderstanding between Lockheed Martin and NASA's Jet Propulsion Lab. One used imperial units, the other used metric. And somehow, in a place full of literal rocket scientists, no one double-checked. This wasn't a programming error. It wasn't sabotage. It wasn't some impossible-to-detect glitch hiding in the software. It was just two people using different units and not saying anything about it, like two chefs cooking the same soup, but one is using teaspoons and the other is using cups. The end result? Disaster stew. Now you might be asking, did anyone get fired for this? Surprisingly, no. NASA didn't go on a firing spree. They did an investigation. They took it seriously. But they understood something important. Blame doesn't fix math. Only better systems do. So they changed their process. They created more checks, more communication, more documentation, because once you lose a spaceship over a unit conversion, you really don't want to do that again. And honestly, that's kind of inspiring. Because the point of math, real math, isn't to be perfect. It's to learn. Every mistake tells us something. Even the expensive ones. Especially the expensive ones. And maybe that's the real lesson here. Not don't make mistakes. You will. I will. We all will. The lesson is, make better ones next time. Okay, so we've mentioned this mysterious thing called a Newton a few times now. No, not the cookie. No, not the guy with the apple. Well, actually yes. Kind of both. But mainly, we're talking about the unit, the Newton, spelled with a lowercase n when you're writing it in a physics textbook, but always deserving of a capital N in your heart. So tonight, let's slow down and ask the question no one dares to ask in public anymore. What is a Newton? You hear it tossed around in space documentaries and science class. It takes this many newtons of force. This rocket generates however many thousands of newtons. Everyone nods like they get it, but inside, we're all thinking the same thing. Cool, but what the heck is it? Let's keep it simple. Newton is a unit of force. It measures how much push or pull is being applied to something. If you push on a shopping cart and it moves forward, that's force. If gravity pulls your toast off the counter in the most dramatic way possible, that's also force, and both can be measured in newtons. 1 newton is defined as the amount of force required to accelerate 1 kilogram of mass by 1 meter per second. In simpler terms, imagine holding a small apple, about 100 grams. Now imagine gently tossing it, so it starts moving a little faster. That push you gave, that's about 1 newton of force. Yes, apples are back. It's all connected. Now let's bring in the legend behind the name Sir Isaac Newton himself. Isaac Newton was the kind of guy who made other smart people feel a little insecure. He basically invented calculus in his spare time, figured out gravity, and then casually wrote the laws of motion that still guide rockets, roller coasters, and toddlers falling off beds. And he did all this while wearing a wig, like a full-on, powdered, 1600s drama wig. He wasn't just brilliant, he was annoyingly brilliant. Legend says he was sitting under a tree one day when an apple fell on his head, and that's what gave him the idea of gravity. That's the version we tell kids, because it sounds whimsical. The truth is probably less dramatic. More like, he saw an apple fall, thought, and then spent months obsessing over why things fall at all. Then he wrote down some equations and changed the world forever. His big idea was this: force equals mass times acceleration. F-E-M, 3 symbols. That's it. But those 3 little characters have powered everything from cars to rockets to robotic vacuum cleaners.
You apply a force to something. It accelerates. The more mass it has, the more force you need to get it moving.
This equation is where the Newton comes from. It's the natural unit for this relationship. Mass in kilograms. Acceleration in meters per second squared. Result: force in newtons. So when we say a spacecraft thruster generates 500 newtons of force, we're saying it's applying enough push to accelerate a 500 kilogram object by 1 meter per second every second. Or a smaller object, much faster. Rockets don't mess around. Let's bring it back to our poor Mars climate orbiter. The data that got misread was about impulse, which is basically force applied over time, like a thruster firing for a few seconds. If the force is in pound force seconds, and you treat it like Newton seconds, your math is wildly off. And that's where this all ties together. The Newton isn't just a unit, it's a language. It tells machines how hard to push, and for how long. It's math turned into action. And if you get the language wrong, things go sideways, or down. Let's have a bit of fun. Here are some things that equal 1 newton of force. The weight of a small apple, the force you feel when a piece of paper rests gently on your hand, the amount of force it takes to pick up a hamster, a chill hamster, not one of the fast, bitey ones. That might not sound like much, but stack enough of those together and you can send a satellite to Jupiter. Now here's a cool twist. Even though Isaac Newton has a unit named after him, he never actually used it himself. He died in 1727. The system Newtons belonged to didn't exist yet. In Newton's time, people measured force in pounds and stones and whatever else they had lying around. This cart weighs 7 goats and half a barrel of ale. It wasn't until the 20th century that scientists said, hey, this guy pretty much invented motion. Let's name a unit after him. And so the Newton was born. It's not the only unit named after someone, by the way. There's the Watt, named after James Watt, the guy who improved steam engines. There's the Joule, named after James Prescott Joule, who sounds like a villain but was actually quite helpful. The Kelvin is for Lord Kelvin, a man who was really into thermodynamics and probably not that into hugs. In science, naming a unit after you is like getting your jersey retired. It means you did something so important, no one's allowed to forget it. Ever. So here we are. The orbiter was guided by data. That data used force. The force was measured in units. The units were assumed. The assumptions were wrong. And the spacecraft went missing. All because of the Newton. Or rather, the lack of the right Newtons. But the Newton itself? Still a hero. Still out there silently calculating how much push is needed to open a door, or fire a rocket, or lift your cat off the keyboard. And that's what makes math so powerful. It takes invisible forces, things we can't see, and gives them names, definitions, equations. It turns mystery into clarity, unless, of course, someone forgets which unit they're using. Okay, so you've learnt about Newtons, you've met Isaac, you've heard the tragic tale of the Mars climate orbiter, and how a mismatch between metric and imperial units turned a scientific dream into a very expensive ghost story. You might be thinking, alright, I get it. Unit conversions are important. We messed up one time. Let's move on. Oh no. No. Because unit conversions are sneakier than you think. They hide in plain sight. They pretend to be harmless. But the moment you stop paying attention, boom, you've got a collapsed bridge, a lost satellite, or worse, a kitchen disaster involving way too much salt. Let's begin with a simple question. Why are there two systems anyway? Why is half the world using metric with meters and liters and kilograms, and the other half is still clinging to miles and gallons, and whatever an ounce is? The short answer? History. The long answer? Human stubbornness. The metric system was invented in France during the 1700s. It was part of this beautiful Enlightenment era dream, where everything would be logical, decimal-based, and standardized. One system for everyone. Scientists loved it. Engineers loved it. The rest of the world eventually kind of shrugged and said, sure, why not? Except for one country.
You guessed it.
The United States of America.
To be fair, they tried. In the 1970s, there was a big push to go metric. Road signs were changed. Schools taught both systems. There were even commercials, like weird 70s-style public service announcements. Go metric, man. But the public didn't like it. It felt weird, un-American. People didn't want to buy milk in liters or measure their kids in centimeters, so they gave up, and the US became the only major industrial nation still using the imperial system. Forever. Alone. Proud. Confused. Now here's the problem. When two systems exist side by side and people assume they're talking about the same thing, disaster strikes. Let's go back to 1999. The Mars orbiter story wasn't the first time this happened, and it wasn't the last. Want another one?
Okay, let's talk about a Canadian airplane. The year is 1983. The flight, Air Canada 43. The destination nowhere, because it ran out of gas mid-air.
Here's what happened. The ground crew calculated how much fuel to load, but they used pounds instead of kilograms. The airplane got half the fuel it needed. Half. Imagine ordering a pizza and only getting the crust. That's how the pilots felt at 35,000 feet. So the engines shut down. Both of them. Total silence. Luckily, the pilot was a trained glider pilot. He managed to land the plane safely on an old abandoned airstrip that used to be a drag racing track. Seriously, you can't make this stuff up. The plane was nicknamed the Gimli Glider, and everyone survived. But the cause, you guessed it, a sneaky unit conversion. Let's go smaller. Ever cooked a recipe you found online and had no idea what a cup meant? Or a stick of butter? Or how many tablespoons are in a fluid ounce? Spoiler, it depends where you live. In the US, a cup is about 240 milliliters. In Australia, slightly different. In the UK, they don't even use cups, they use grams, milliliters, and chaos. So if you're cooking something international and don't convert the units properly, you might end up with soup when you wanted bread, or worse, British scones when you wanted cookies. And let's not even start on temperature. Fahrenheit versus Celsius is just rude. 32 degrees in Fahrenheit is freezing. In Celsius, 32 degrees is the inside of a toaster. People have walked outside thinking it was a nice day, only to spontaneously combust. Okay, maybe not literally, but still, let's also talk about speed. Miles per hour versus kilometers per hour. You see 100 on a sign in Europe and think, whoa, we're going fast. But no, it's kilometers, which means you're just doing about 60 miles per hour. Relax. You're not Vin Diesel. All of this creates confusion. And confusion leads to mistakes. And mistakes, as we've learned, lead to spacecraft flying into planets like they forgot to wear seatbelts. The core issue is this: numbers without context are dangerous. A 5 can mean anything. 5 apples, 5 kilometers, $5, 5 nuclear warheads. Without the unit, the number is just floating. Empty. It's like sending someone a package with no label. They might think it's cookies. It might be a live snake. And even when the unit is there, if someone's brain is still thinking in another system, disaster is still possible. This is why scientists love the metric system. Not because it's cooler, but because it's clear. Base 10. Everything connects. Easy to convert. Easy to scale. It's like math with manners. But when you mix systems, when you bring imperial and metric to the same party, someone's going to spike the punch. That's what happened with the Mars Climate Orbiter. The thruster data was sent in pound force seconds. The navigation team read it as Newton seconds. They assumed they were speaking the same language, and they were. It's like trying to follow GPS directions that say turn right in 2 kilometers, and you respond by turning in 2 feet. You're in a ditch before the system finishes recalculating. And here's the most important part. It's not just about space. Unit conversion errors affect everything. Medicine, engineering, finance, aviation, cooking, manufacturing, even fashion. If you've ever tried to order pants from another country and ended up with what felt like dull clothing. So, what can we do? Simple. Slow down. Double check. Ask questions. Never assume that 5 means the same thing to everyone. Always ask what the unit is. Always confirm you're using the right system. And never let close enough be your final answer. Math will forgive a lot of things. But unit confusion? That's personal. In our next chapter, we'll take a stroll through math mistakes throughout history. Not just unit conversions, but the kind of tiny errors that brought down buildings, failed missions, and sometimes changed the world. But for now, take a moment to appreciate how weirdly impressive it is that humans can send objects across millions of kilometers, and that the biggest threat to success is still forgetting to carry the one. Math has given us a lot of beautiful things. Satellites, electricity, cat videos delivered instantly to your phone. But tonight, let's take a moment to appreciate the other side of math. The part where it goes horribly wrong. Because while math is logical, humans are not. And when you mix perfect logic with imperfect people, you get stories, big stories, historical stories, mistakes that left buildings swaying, missions failing, and a few very panicked engineers staring at clipboards going, wait, Let's go back in time. First up, the year 1990. The place, Vancouver, Canada. An architect designs a fancy new building. Sleek, modern, lots of glass. The kind of place where you'd expect to see someone wearing a turtleneck and sipping espresso. But when the building was nearly done, people started noticing something weird. It moved. Not in a fun, magical castle way. More like a why is the floor shaking kind of way. Turns out the architect had forgotten to account for wind load. That's the sideways pressure wind puts on a tall building. It's kind of important, especially if you don't want your office tower to dance during storms. The fix? They had to install massive tuned mass dampers, basically giant weights to stop it from wobbling like a drunk giraffe. Cost? Millions. Reason? Bad math. Let's go older. Back in 1981, there was a missile system called the Patriot. It was designed to track and intercept incoming threats with very precise timing. But during the Gulf War in 1991, a Patriot battery failed to track an incoming missile. It missed. The result? The missile hit a US base, and 28 soldiers died. The reason? A software bug caused the system's internal clock to slowly drift off by just 1/3 of a second. You know what caused that drift? A math error in how the computer rounded decimal places. Just one little rounding mistake. Not a bad design. Not sabotage. Just a few tiny digits that weren't quite right. And that led to lives lost. Let's jump to construction again. 1983, Kansas City. There's a beautiful hotel with skywalks, basically suspended walkways hanging above the lobby. Elegant. Fancy. Great for people watching while pretending to be on a business call. Then one day, 2 of the walkways collapsed during a dance event. Right into the lobby. 114 people died. Over 200 were injured. What happened? The original design called for one long rod to hold up both walkways, but the construction team changed it without running the full calculations. The result? Double the load on the upper walkway. It couldn't take it. The math wasn't rechecked, and the structure failed. We're not done. Let's talk about NASA again, because apparently they have a whole collection of math mistakes. In 1962, during the Mariner 1 mission to Venus, the rocket exploded shortly after launch. The cause? A missing hyphen in the guidance software. Yes? A hyphen. Someone forgot to put it in the code, and the result was a faulty trajectory that triggered self-destruction. The press called it the most expensive hyphen in history. Which is kind of funny, and also completely horrifying. Sometimes it's not just math, it's human pride. In the 1990s, the European Space Agency launched the Ariane 5 rocket. First launch, big expectations, lots of champagne on standby. 37 seconds after takeoff, it exploded. Why? Because some of the software from the earlier Ariane 4 system had been reused without updating the math to handle the new rocket's faster speed. A number got too big for the computer to handle, and it crashed. Literally. Cost over $370 million. Again, a number. A single number. Too big. No error handling. Boom. Let's go even deeper. In 2007, a bridge in Minnesota collapsed suddenly. During rush hour, 13 people died. Investigations found that a key support plate was too thin. The original design used calculations that didn't fully account for how much load the bridge would carry over time. And yes, that included rush hour traffic, construction equipment and layers of snow, because someone underestimated the math behind how heavy life can be. You might be wondering, how does this keep happening? The answer is simple. Math, when done correctly, is exact. But humans are not always so careful. We forget parentheses. We misplace decimals. We assume. We round. We say good enough when we're tired and under deadline. And that's when things break. It's not that math failed. It's that someone told it the wrong thing. You can have the most powerful equations in the world, but if your input is wrong, your output will be worse. It's like giving a GPS the wrong destination. and wondering why you ended up at a clown convention.
And it's not just about cost. It's about lives, trust, reputation, safety.
So the next time someone rolls their eyes in math class and says, "When will I ever use this?" well, you can gently remind them that one day they might build a bridge, or write a line of code for a rocket, or design a skyscraper, or, try to land a spacecraft on Mars. And if they're not careful, the math will remember. Now, this might all sound dramatic, but it's not meant to scare you. It's meant to show you just how powerful math really is. It's not just symbols and numbers on paper. It's real. It builds our world. It launches rockets. It keeps airplanes in the sky. It's the invisible language that keeps everything from collapsing. Unless, of course, someone forgets a hyphen. So far, we've talked about mistakes. Some hilarious, some tragic, some that cost more than the entire budget of a small country. But tonight, let's take a softer turn. Let's talk about something humans have never really been able to explain. Not with equations, not with physics, not even with really aggressive TED Talks. Let's talk about our strange, persistent obsession with Mars. Because here's the thing, we keep going back. We've sent orbiters, landers, rovers, probes, you name it. If we could send a pizza, we probably would. Mars is like the ex we can't stop texting, even after it ghosted us, sometimes literally for years. But why? Why that planet? Why not Venus? Or Mercury? Or Jupiter's moon that might have oceans? Let's explore that gently. Mars is the fourth planet from the Sun. It's cold, dry, covered in rust, which is why it looks red. It's not blushing, it's oxidizing. Its atmosphere is 96% carbon dioxide, which means you'd suffocate immediately if you tried to breathe there. It has no magnetic field, which means radiation rains down from the sun all the time. Its dust storms can last months and cover the whole planet, and the average temperature around minus 60 degrees Celsius. So, not exactly vacation material, and yet, we're obsessed. We name candy bars after it. We write books about it. We make movies about being stranded on it and growing potatoes in poop soil. We put little flags on computer-generated Martian soil and cry like proud parents when a robot lands there. Mars gets all the attention, and the obsession is ancient. The Babylonians tracked Mars as early as 400 BCE. They called it Nergal, named after a god of war and destruction. Cheerful. The Romans, of course, named it after their god of war, Mars, which stuck. Because it was red. Because it looked angry. Because ancient people saw a glowing red dot in the night sky and thought, that thing is definitely up to something. Even in ancient India, Mars was associated with aggression and conflict. In Chinese astronomy, it was known as the fire star. Basically, everyone looked up and thought, that one's dangerous. And somehow, that made us fall in love with it. Fast forward a couple of centuries and along comes a guy named Percival Lowell, an American astronomer who believed he saw canals on Mars through his telescope in the late 1800s. Canals, like waterworks. Artificial ones, built by intelligent beings. Spoiler, he was wrong, but the idea stuck. Science fiction exploded. Stories about Martians invaded bookshelves and movie screens. H.G. Wells wrote The War of the Worlds, where Martians invade Earth. They had death rays. Naturally. Later, we sent our first probes. The early missions mostly failed, because Mars is tricky. It's like trying to throw a dart across a football field, blindfolded, while the dartboard is moving and on fire. But eventually, we succeeded. In 1976, Viking 1 became the first US spacecraft to land successfully on Mars and send back photos, black and white, grainy, a little boring, but deeply emotional. Humanity had touched another world. And then came the rovers. Sojourner, Spirit, Opportunity, Curiosity, and most recently, Perseverance. Each one more advanced than the last. Each one with a personality. We gave them Twitter accounts. We cried when they stopped responding, especially Opportunity, which operated way longer than expected. Its final message, after a dust storm knocked it out: "My battery is low, and it's getting dark." Oof. Right in the feelings. So why are we so attached to this place? Why Mars? Part of it is that it's close. Not close like next door neighbor, but in cosmic terms, it's the best real estate we've got outside Earth. Not too hot, not too cold, not made of gas, not covered in acid rain, just Mars. It's also similar in some ways. Mars has seasons. It has polar ice caps. It has canyons, volcanoes, and valleys. It has day and night cycles that are nearly the same as ours. A Martian day, called a sol, is just about 40 minutes longer than an Earth day. So if you moved there, you'd just need to reset your watch and wear a spacesuit forever. But the real reason, hope. Mars is the one place that makes us ask, could we live there? Could we build something? Grow something? Start over? It's not about escape. It's about curiosity, about exploration, about proving to ourselves that we can go beyond, that we're not stuck here, that our brains, our math, our wild little species, we're capable of more than just arguing on the internet. Mars is a symbol, a goal, a depth, and sure, it's full of dust and radiation and rocks that don't care about your feelings, but it's also full of mystery. We still don't know if it once had life, or water, or bacteria wearing tiny Martian sunglasses. We just know we want to find out. And math, of course, is how we get there. We use it to design the rockets, plot the courses, time the launches, navigate the landings. We send numbers into space, and they come back as photos, sounds, data, and maybe, someday even people. Math is the quiet engine behind our obsession. The reason it's possible, the reason we keep trying. Even after failure, after mistakes, after crashing into Mars and making very expensive craters. Because one day, maybe, we'll get it right. One day we'll plant a flag, not as a claim but as a symbol, that we're still reaching, still dreaming, still curious, and that, more than anything, is what makes us human. So, you want to go to space? Great. Pack some snacks. Maybe a sweater. It gets cold out there, but before you launch yourself into the void, there's something we need to figure out first. How do you get anywhere in space without getting lost? Because here's the thing, space is huge. Like beyond huge. We can't even come up with good metaphors for it. It's just big, empty, and always moving. And somehow, we managed to send spacecraft across millions of kilometers of this swirling chaos and actually arrive at the right place. We land on Mars. We orbit Saturn. We visit comets that are moving at 100,000 kilometers per hour. We do all of this with one thing, math. You can't just point a spaceship and hit go. That works in cartoons, not in real life. In real life, everything is in motion. Earth is spinning, Mars is spinning, the sun is pulling everything around it like a DJ with a gravity playlist. Even the spacecraft itself starts drifting the moment it leaves Earth's pull. So how do we do it? We plan. Precisely. Let's start with orbital mechanics, the math of how things move through space. There's a beautiful little rule called Kepler's laws. These were figured out by Johannes Kepler back in the early 1600s. Before space travel was even a thing. The guy just looked at planets and said, you know what? These orbits aren't circles, they're ellipses. And he was right. Kepler's laws tell us how fast a planet moves, how long it takes to go around the sun, and how far away it is. These rules gave us the framework to understand motion in space. Then Newton came along with his whole force equals mass times acceleration thing. And suddenly we had a recipe for predicting movement. You apply a force, and you can calculate exactly where the object will go, how fast, in what direction, how it'll curve. These laws haven't changed. What has changed is our ability to calculate faster, and with more precision. Let's say we want to send a probe to Mars. We can't just fire it directly at where Mars is now, because by the time the spacecraft gets there, Mars will have moved. It's like trying to throw a paper airplane at a running target, while you're also running. So we do something called a Hohmann transfer orbit. It's the most fuel-efficient path between two orbits. Think of it like a cosmic slingshot. You time your launch just right, burn your engines just right, and then coast along an elliptical path that intercepts Mars when it arrives at the same point. It's not intuitive. You actually launch toward where Mars will be months from now. The whole thing feels like you're trying to catch a train by mailing yourself to the next station in advance. And the math. It's beautiful. It involves gravity, mass, timing, and velocity. Lots of velocity. Once you're in space, you don't need to keep the engines running. You just coast. That's the magic of inertia. Unless you hit something, please don't, or get pulled by another planet's gravity. Also not great. You'll just keep going. But if you do need to adjust, say you're drifting off course, you perform a course correction. This is where the math gets spicy. You calculate your current position, your velocity, your intended path, and the amount of thrust needed to get back on track. And you do this with extreme precision, because fuel is limited, and overcorrecting means wasting energy. Even the smallest adjustment, a 0.1 degree angle, can mean the difference between hitting Mars or flying past it into deep space forever. Like that one time you missed your bus stop and ended up in a town you didn't know existed. That's why spacecraft have onboard navigation systems. These include gyroscopes, star trackers, accelerometers, tools that let them know exactly where they are and where they're going. Star trackers are particularly cool. The spacecraft looks at the stars, literally takes pictures of the sky, and compares what it sees to a star map stored in its memory. It's like the spaceship is stargazing and going, "Ah yes, I must be over there." Once it knows where it is, the onboard computer can calculate whether it's on the right path. If it's not, it sends a signal back to mission control. And if mission control agrees, the spacecraft gets new commands. Or, if it's advanced enough, it adjusts itself. It's all math, angles, vectors, thrust to mass ratios, delta V calculations. That's the amount of change in velocity needed to perform a maneuver. It's like space ballet, but instead of dancers, you have a metal robot spinning silently through the void with nothing but numbers to guide it. One of the most mind-blowing things. We navigate all this across a time delay. When you send a command to a spacecraft near Mars, it can take up to 20 minutes to arrive. Then it takes another 20 minutes to hear back. So if something goes wrong, you can't just joystick your way out of it, like a video game. The math has to be done beforehand. The system has to be ready, autonomous, pre-programmed, calm. There's no margin for panic. Think of it like planning a road trip, but you have to program the entire route, the bathroom breaks, and the Spotify playlist before you even leave the driveway. And if you turn left at Albuquerque by mistake, well, see you in Pluto. But the amazing part? It works. We've landed rovers on Mars using this math. We've sent spacecraft to the edges of the solar system. We've dropped probes onto comets, zipped past asteroids, and even landed on Saturn's moon, Titan, which, by the way, has methane lakes. Because why not? All of it. Because of math. And it's not magic. It's just persistence. Logic. Patience. A million calculations done carefully, tested, and then trusted to perform alone in the middle of nowhere. And it works. That's the beauty of it. So the next time someone says math is boring or useless, or just something you suffer through in school, remind them that math is literally how we explore the universe. Quietly. Exactly. Reliably. If there's one place on Earth where you'd expect every single detail to be double, triple, and quadruple checked, it's NASA. These are the people who sent humans to the moon using computers that were less powerful than your microwave. They land robots on planets hundreds of millions of kilometers away. They fling telescopes into space. perfectly aligned to photograph galaxies that haven't even RSVP'd to existence yet. In short, NASA is known for being precise. But even at NASA, mistakes happen. Let's zoom in a little. NASA, the National Aeronautics and Space Administration, is made up of thousands of scientists, engineers, mathematicians, programmers, technicians, and very tired interns. They build spacecraft, test rocket engines, simulate alien dust storms, and write mission plans so detailed they include how much torque to apply to a bolt. In this world, everything is measured. Everything is documented. There are checklists for the checklists. There's probably a spreadsheet somewhere listing all the other spreadsheets. Why? Because space doesn't forgive mistakes. You can't run back to the lab when something breaks. You can't call roadside assistance. You can't say oops and fix it with duct tape and prayer. You either got the math right, or the spacecraft is now a permanent moon ornament. And for the most part, NASA gets it right. Stunningly right. They've launched hundreds of missions, many of them so successful, they go far beyond their intended lifespan. The Voyager probes were launched in 1977 and are still sending back data from interstellar space. But here's where it gets interesting. Because when NASA does make a mistake, it usually isn't because they forgot a decimal or didn't know the math. It's almost always because of something more human. Assumptions, communication breakdowns, too many people in different rooms speaking slightly different languages. Not English versus French, but engineer speak versus programmer speak versus scientist speak. Let's go back to our story. The Mars Climate Orbiter. This was a joint mission between NASA's Jet Propulsion Laboratory and Lockheed Martin, a private aerospace company. Lockheed was responsible for some of the software, including the bit that calculated the force from the thrusters. JPL, meanwhile, was handling navigation, figuring out where the spacecraft was going, and how to keep it on course. Now remember, Lockheed's software was outputting pound force seconds. An imperial unit, JPL, naturally assumed it was getting Newton seconds metric, and nobody noticed the mismatch. Nobody said, hey, just to be sure, what unit are we all using here? Why? Because both teams were brilliant. Because both had done this before. Because everyone assumed someone else had confirmed it. And that's the quiet danger inside even the most precise cultures. Assumptions feel safe when you're surrounded by smart people. NASA later called this a failure of system engineering and the checks and balances in process. Translation: the system was supposed to catch the mistake and did. There were no automated checks for unit compatibility. There was no built-in alert that said, hey, this number seems weird. The software did exactly what it was told. And so, the spacecraft did exactly what the software told it to do. And that, of course, ended with a high-speed atmospheric belly flop into Mars. After the failure, NASA took it seriously. They ran internal reviews. They released a report. They didn't just say oops, they said never again. They changed procedures. They implemented better communication protocols, more formal handoffs between teams, required unit documentation, mandatory checks on data formatting and assumptions. In other words, they adjusted the culture, because they understood something critical. You can't prevent all mistakes, but you can design a system that's better at catching them. And that's kind of beautiful.
NASA's obsession with precision isn't about being perfect. It's about being humble.
They build missions on the assumption that things might go wrong. They add redundancy, backup systems, layers of verification, not because they don't trust their people, but because they trust that even the best people are still people. They know that in a room full of geniuses, the biggest danger isn't stupidity, it's overconfidence. And yet, despite the failures, NASA keeps going. They keep launching. They keep calculating. They keep building rockets with math so clean it might as well wear a tuxedo. Because the goal isn't perfection. The goal is progress. Learning, improving, trying again, with better equations, better systems, better teamwork. The Mars Climate Orbiter became a case study. Not just in math errors, but in how smart organizations handle mistakes. With honesty, with process, with the understanding that space will always be a little bit unpredictable. And our best defense is math, teamwork, and a culture that's not afraid to admit when something goes wrong. There's a reason NASA is still the gold standard. It's not because they never mess up. It's because they learn, adapt, and make sure the next mission is safer, stronger, and smarter. In fact, the very next Mars mission, the Mars Polar Lander, had even stricter protocols. Later rovers like Spirit, Opportunity, and Curiosity were launched under tighter engineering supervision. And they worked because NASA knew the price of imprecision in space isn't just money, it's progress. So next time someone tells you that being a perfectionist is a bad thing, just whisper softly, NASA triple checks its decimals, and so should I. Let's be honest, we humans are not exactly known for being error-free. We forget birthdays. We burn toast. We accidentally hit reply all. Some of us still don't know the difference between your, and that's okay. Kind of. But when humans make mistakes in math, especially in engineering, science, or space, things get a little more dramatic. The stakes go from oops, I left the oven on, to oops, I just tilted a satellite into the void. It's tragic. It's expensive. And sometimes it's also really, really funny. Tonight, let's walk gently through some of the most delightfully human math blunders in history. Mistakes that didn't come from stupidity, but from assumptions, habits, bad habits, and one too many late nights at the calculator. Let's start with a classic. NASA, the mission was supposed to launch from Cape Canaveral, dock with another spacecraft, and prove that humans could maneuver in space, but the launch was aborted at the last second. The engines had already fired. Why? Because one engineer forgot to plug in a tiny wire correctly. That one wire sent the wrong signal and caused the whole rocket to shut down automatically. No one died. The rocket was fine, but the moment became legendary. Later, when someone asked what caused the abort, an engineer said, "The guy forgot to plug something in." That's it. Years of planning, thousands of calculations, and a guy forgot a wire. Let's fast forward. 1997, the Ariane 5 rocket. This is a big one. The European Space Agency was launching a brand new rocket. Years of development, hundreds of millions of euros. Confidence levels were sky high. Then 37 seconds after liftoff, it exploded. What happened? Well, they reused a piece of code from the Ariane 4 rocket. Only this time, the numbers were bigger. The software tried to store a value that was too large for the variable. The computer crashed. The rocket veered off course. And boom, all because of a data overflow. A fancy way of saying, the number was too big for the box. It's like trying to stuff a mattress into a suitcase. The suitcase explodes, your vacation is cancelled. The worst part? The software that caused the crash wasn't even needed during that part of the flight. It was just running, in the background, doing its thing, until it got confused, panicked, and brought the whole rocket down with it. But it's not just space where the comedy of math errors plays out. Let's talk about money. In 2005, a Japanese trader tried to sell one share of a stock for 610,000 yen. Instead, he accidentally sold 610,000 shares for 1 yen each. That's about $5 million. Gone in minutes. And the best part, the company tried to cancel the trade, but the Tokyo Stock Exchange said, "Sorry, the transaction is already complete."
One click, one tiny switch. Millions evaporated.
And he wasn't the only one. In 2014, a bank in Germany accidentally transferred 222 million euros because a sleepy employee fell asleep on the keyboard. Their hand got stuck on the number key while entering a transaction. That's not a joke. They literally napped their way into a bank error. Now let's talk planes. In 1983, yes, again, an Air Canada Boeing 767 made aviation history, not for its sleek design, not for its record speed, for running out of fuel mid-flight? This was the famous Gimli glider incident. You've heard part of the story before, but let's zoom in on the human side. Two teams, one calculating how much fuel was needed and one putting it into the plane, used different units. One used pounds, one used kilograms. No one caught the error. The plane ran out of fuel, the engines died, the pilots glided it like a giant, slightly terrified paper airplane down onto a closed airstrip that was being used for car races. Yes, car races. They landed safely. No one died, but it's still considered one of the most impressive oops recoveries in aviation history. And it all happened because, again, no one asked, wait, what unit are we using? Are you starting to notice a pattern? Humans don't make math mistakes because we're bad at math. We make them because we're bad at checking things we think we already know. Because we assume. Because we're tired. Because it's Monday. Or Friday. Or because someone mumbled the wrong number into the room, and everyone nodded like they understood. And because we're busy, oh, so busy. In fact, busyness might be the real villain in this whole tragic comedy. Most of the great math mistakes in history happened not because the math was hard, but because there wasn't enough time or attention or curiosity left to double-check the work. We assume the formula is right. The software is clean. The spreadsheet is formatted. The wire is plugged in. But the thing about math is, and I say this with love, it doesn't care what you assume. It only cares about what's actually there, what number you typed, what unit you used, what decimal you rounded. If you told math to divide by 0, it's not going to argue. It'll just shrug and collapse the entire simulation. Now, does this mean we should fear math? Absolutely not. It just means we should respect it. Because math is kind of like a very chill robot roommate. It doesn't yell. It doesn't judge. It just listens and does exactly what you ask it to. Even if what you asked for is, hey, could you destroy this spacecraft really quick because I forgot a unit? It will. No questions asked. So, the Mars Climate Orbiter was gone, vanished somewhere in the Martian atmosphere, or maybe skipped off it like a flat rock on a cosmic pond. No photos, no data. Just silence. NASA's $327 million mission had quietly turned into one of the most expensive oops moments in space history. Now comes the natural question. Who got blamed? Because when something expensive explodes, even invisibly, people start pointing fingers. Managers get nervous. Engineers start double-checking emails. And someone somewhere is suddenly very interested in finding out who forgot to convert the units. But the story of what happened after the orbiter disappeared is actually kind of surprising. Let's walk through it. First, NASA launched a formal investigation, as they should. They weren't looking for a villain in a lab coat. They wanted to understand how this happened, because deep down, they knew something bigger than a single person had gone wrong. And they were right. The Mars Climate Orbiter Failure Review Board released their final report not long after the mission was lost. It didn't read like a Hollywood screenplay. There was no aha moment, no dramatic betrayal, no evil scientist whispering, I used pounds instead of newtons, and now no one can stop me. Nope, instead it was painfully mundane. The Lockheed Martin engineering team, which developed the spacecraft software, was outputting thrust data in pound-force seconds, a perfectly valid imperial unit. Meanwhile, NASA's Jet Propulsion Laboratory, JPL, assumed the data was in Newton seconds, the metric version. The software didn't throw an error. The navigation system didn't question it. No one cross-checked the unit documentation. No one built a failsafe into the system that said, hey, are you sure this data is in newtons? It just passed through. Quietly. Smoothly. And that's what doomed the spacecraft. So, who got fired? No one.
That's right.
No one lost their job. No dramatic firings. No courtroom drama. No engineers walking out of NASA headquarters carrying cardboard boxes and crying softly over their calculators. Why? because NASA understood something that most organizations struggle with. This wasn't a single person's fault. It was a systemic failure. A failure of communication. A failure of process. A failure to assume less and confirm more. NASA called it a failure of system engineering and the checks and balances in the process, which is a very professional way of saying we were too busy, too confident, and too disorganized to notice a tiny, deadly mismatch. If they had just asked, hey, what units are we using? At any point, literally any point, the disaster could have been avoided. But they didn't, because they trusted the system, and the system trusted them back, and nobody questioned it. This is what makes the story both frustrating and kind of beautiful, because NASA didn't just look for someone to blame. They looked for ways to never let it happen again. After the incident, they made changes. Serious ones. They implemented mandatory unit checks between teams, created clearer documentation standards, improved their software testing processes, made sure that unit assumptions were never left hanging in the air like a decimal on a windy day. They didn't just patch the hole, they redesigned the whole floor around it. And here's something else to think about. The engineers involved in the Mars Climate Orbiter project were incredibly smart. We're not talking about amateurs. These were some of the most experienced minds in the field, people who had worked on dozens of missions before, people who had built hardware that actually worked in space, and they still missed it, because brains aren't enough. You need structure. You need process. You need someone in the room to raise their hand and say, wait, what unit are we talking about here? And you need to create a culture where that question isn't annoying, where it's welcomed, encouraged, expected. NASA took responsibility for the fact that the question wasn't asked. They didn't blame the software team. They didn't point at JPL and yell. They just admitted, we didn't build a system that caught the mistake. That's on us. Honestly, that takes guts, because it's way easier to find a scapegoat, fire one person, tell the press, problem solved. But NASA knew that if they wanted to keep exploring space, they had to explore their own systems just as fearlessly. They had to learn, and they did. The very next missions, like the Mars Odyssey and the Spirit and Opportunity rovers, had much tighter systems, better communication, more robust unit checking. And those missions, they succeeded. In fact, Opportunity, which was only meant to last 90 days, kept rolling for almost 15 years. Because NASA learned from its mistake, they didn't hide it. They published it. They turned the Mars Climate Orbiter into a case study. Engineering students still learn about it today. Not to laugh, not to shame, but to remember, it's not always the complex equations that ruin a mission. Sometimes it's just forgetting to ask one small question. So, no, nobody got blamed in the dramatic way we might expect. But everyone took responsibility, and that might be more powerful. Because in science, real science, the point isn't to be perfect, to make failure useful, to fall forward. And hey, if you ever do make a mistake at work, just remember, unless you've lost a spaceship by mixing up pounds and newtons, you're probably doing okay. Alright, we've danced around it for a while now, but it's finally time to talk about the measuring systems themselves, because at the heart of the Mars Climate Orbiter disaster, and many, many others, is an ancient rivalry, a battle between two systems, two ideologies, two units that just couldn't get along. Yes, I'm talking about metric versus imperial, a civil war fought with tape measures and thermometers, a decades-long staring contest between millimeters and inches. So, let's dim the lights, lower the volume, and gently settle into the world's most polite math argument. Let's start with the metric system. Born in France during the late 1700s, the metric system was created during the French Revolution, that fun little moment in history when people decided, you know what, let's stop chopping heads off and start measuring things better. A system based on powers of 10. 1 meter, that's 100 centimeters. 1 kilogram, that's 1,000 grams. Need to convert something? Just move the decimal. It's math, but with training wheels. Then, on the other side of the measuring battlefield, we have the imperial system, or, as some people lovingly call it, the system that makes no sense but we're emotionally attached to it. This one came from England, and then hitched a ride across the Atlantic to the United States, where it put its feet up and never left. In the imperial system, there are 12 inches in 3 feet in a yard. Kill. 1,016 ounces in a pound, and 1 to. Why? No one knows. Some say it's tradition. Some say it's because old British merchants had weird hands and cups and decided, yeah, let's use this forever. Now, here's the part that makes this rivalry truly special. Almost the entire world uses the metric system. All of Europe, most of Asia, Australia, South America, Africa, the international scientific community, the Olympic Games, NASA, medicine, engineering, literally most humans on the planet, except the United States. America is the only industrialized country still using the imperial system in everyday life. Feet, miles, gallons, Fahrenheit. It's like the US is at a potluck dinner where everyone brought metric casseroles and America walks in with a measuring cup and says, "This is a tablespoon. Trust me." To be fair, the US does use metric in some places. Science, medicine, the military, soda bottles, but everyday life, inches, miles, ounces. So why hasn't the US switched? Well, they tried. In the 1970s, there was a movement to officially convert the US to metric. The government passed the Metric Conversion Act. Road signs were replaced. Schools started teaching it. Metrication was happening. And then, it just kind of fizzled out. Why? Because people didn't like it. They were used to measuring their height in feet, their weight in pounds, their weather in Fahrenheit. Switching felt weird. It felt un-American. So the movement slowed down, then stopped. And now we live in a world where Americans drive 65 miles per hour, while scientists quietly whisper, that's about 105 kilometers per hour. But sure, live your truth. Now, here's where the comedy kicks in. Having two systems side by side, metric and imperial causes confusion. Not just casual confusion, dangerous confusion. As you've seen with the Mars Climate Orbiter, mixing up units is a very efficient way to make $327 million disappear. It also confuses students. You ask a kid how tall they are, and they'll say 5'7". Then in science class, they measure things in centimeters. In cooking class, they use cups. In chemistry, it's milliliters. That's like switching languages 3 times before lunch. And then there's Fahrenheit. Or Fahrenheit. In America, 100 degrees Fahrenheit is hot. Like stay inside and drink iced tea hot. In Celsius, 100 degrees is boiling. As in, you are soup now. Meanwhile, 0 degrees Celsius is freezing. But in Fahrenheit? That's why. Again, no one really knows. Some say the creator of the Fahrenheit scale, Daniel Fahrenheit, just kind of made it up using salt water, ice and vibes. He decided freezing should be 32, body temperature around 98, and boiling somewhere near 2, because why not? Compare that to Celsius.
UVLCA freeze.
100. Boiling. It's simple, clean, predictable. But hey, if you grew up in Fahrenheit, Celsius feels cold and distant, like a math teacher who gives too much homework and not enough explanation. The point is, both systems have their fans. Some people love metric because it's logical. Others love imperial because it feels personal, familiar, and deeply baked into their daily life. You don't say, I'm 1.83 meters tall. You say, I'm 6 feet. Unless you're at a European swimming pool, in which case, please convert before you dive in. And look, it's not that imperial is bad. It's just inconsistent. You need a cheat sheet just to go grocery shopping. And if you ever try to explain it to someone from a metric country, their face will slowly melt into confusion. But that's also what makes it kind of charming. It's quirky, old school, like writing checks or owning a VHS player, slightly annoying, but nostalgic. And yet, when it comes to engineering, science and space exploration, most professionals agree. Metric is safer. There's less room for error, fewer weird conversion factors, better consistency across teams and countries. Which is why organizations like NASA prefer metric. It's not because they hate feet and inches. It's because when you're trying to land a robot on Mars, you don't want to convert gallons into liters and pray the numbers agree. You just want math to work cleanly, quietly, without a single missing unit. Math has taken us to space. It's built bridges, powered engines, crashed a few spacecrafts along the way. But here's a secret. Math isn't just hiding in labs, or buried in rocket blueprints, or whispered in dark corners of NASA headquarters. Math is everywhere. In your kitchen, in your car, in your phone, in your favorite playlist, in your awkward text to your crush. It's in the steps you take, the food you eat, the games you play, even the shape of your cat's tail as it curls around your leg. Math isn't just a subject. It's a quiet language running in the background of your daily life, like elevator music made of numbers. Let's start simple. Cooking. Every time you follow a recipe, you're doing math. Fractions, ratios, unit conversions, timing, temperature. Need to double the recipe? That's multiplication. Need to convert cups to milliliters? That's conversion. Need to figure out if your pan is big enough for 1.5 times the lasagna? That's surface area. You're basically a culinary engineer. And your oven is a hot metal calculator. Let's go grocery shopping. You walk down the aisle and see 2 boxes of cereal. One is $4.99 for 500 grams. The other is 6. Without thinking about it, your brain starts calculating which is the better deal. Maybe not perfectly, but instinctively. That's unit price math. Your brain is doing division without permission. And when you hand over money, you're doing subtraction, estimation, rounding. You've been a budget analyst this whole time and never even got the job title. Let's talk about time. You set an alarm for 7:15 a.m. You need to leave by 8 Seren. The shower takes 10 minutes. Breakfast takes 12. You want to scroll your phone for at least 7 minutes like a sleepy goblin. Boom. That's scheduling math. Time management. Estimating backward from a deadline. You're doing algebra in your pajamas. And then there's your phone.
Every app on your screen is powered by math.
Your GPS, trigonometry and geometry. Your camera, pixels and matrices and light intensity equations. Your video stream, compression algorithms. Your favorite social media app, where you scroll endlessly and try not to accidentally like your ex's vacation photo from 2019. Also math, specifically algorithms. Math decides what you see, when you see it, and why it thinks you want more videos of raccoons doing yoga. Which, let's be honest, you probably do. Even texting uses math. Your phone predicts words using probability. It guesses what you're going to say based on frequency, context, and previous patterns. It's basically running thousands of micro-calculations to help you send a single heart emoji and the word lull. Let's go deeper. Love. That's right. Even love has math in it. Dating apps use matching algorithms, probability, game theory, behavioral analysis. They calculate compatibility scores, optimize swiping patterns, and try to predict human chemistry using formulas. Of course, real relationships go beyond numbers, but the math still tries, awkwardly. Like a robot trying to give you a flower. Even in friendships, math sneaks in. Think about group chat. There's always an unspoken rule. How many texts in a row is too many? If you send 3 messages and no one replies, do you send a 4th? What's the ratio of texts to replies before it becomes embarrassing? Congratulations, you've entered the world of social math. What about sports? Watching a game? Stat. Playing a game. Geometry. Angles. Velocity. Timing. Trying to win an argument about which player is better. That's advanced statistical modeling, wrapped in yelling. Even walking uses math. You don't think about it, but your brain is constantly measuring distance, stride length, speed, and balance. If you're walking on a crowded street and somehow avoid crashing into people, that's geometry, physics, and a bit of human intuition. You're a living algorithm in shoes. Now let's go full cozy and talk about baking. Baking is literally edible chemistry and math combined. You need exact measurements, ratios of flour to sugar, leavening agents timed to perfection. You change the temperature by 5 degrees and suddenly your cookies are flat pancakes or undercooked sadness. But when it works, it's math you can eat, and we haven't even touched on music. Yes, music is math. Beats per minute, fractions, scales and chords, patterns and ratios, harmony, frequency alignment. Your favorite songs are just well-structured waves of sound frequencies, bouncing around in beautiful mathematical alignment until your brain goes, yes, this slaps, and then you press replay, and the algorithm smiles. So here's the truth. You don't do math, you live it every day, even if you don't notice, even if you hated algebra in school, even if the word calculus still gives you mild stress hives. It doesn't matter. Math isn't trying to test you. It's just hanging out, helping, quietly solving things in the background. From your oven timer to your phone screen to your heartbeat. Yes, even your heartbeat. Doctors use equations to measure it, track it, diagnose it. Your body itself is a walking math machine. Blood flow, oxygen exchange, pressure, temperature, all mathematical systems working together to keep you alive and binge-watching documentaries. And if that's not poetic, I don't know what is. So the next time someone says, I'm not a math person, feel free to smile gently and say, actually, you are. You're just really good at the secret kind. By now, you and I both know something important. Math doesn't mess around. It's powerful, quiet, unforgiving, like a robot librarian with a steel clipboard. If you give it the right inputs, it'll work wonders. If you give it the wrong ones, well, it'll still do what you said, and then casually break the stock market, or sink a building, or ruin someone's Tuesday. Tonight, let's wander through some more of those moments. The ones where humans forgot to check the math, where a tiny error quietly wiggled its way into a spreadsheet or an equation and changed the course of history, or at least made a very expensive mess. Let's start with one of the big ones, the 2008 financial crisis. There were many causes behind the global financial meltdown, but at the heart of it all was a very simple problem. People believed models more than they believed common sense. Banks used complex mathematical models to package and sell risky mortgages. The math said, don't worry, this is safe, totally normal, practically risk-free. Spoiler, it wasn't. The models didn't account for a large-scale collapse in housing prices. They didn't factor in how many bad loans were floating around, or how interconnected everything was. The risk calculations were off, way off. And when the system cracked, the damage spread everywhere. It wasn't just a financial crisis. It was a math crisis, one caused by assumptions, overconfidence, and a stubborn refusal to say, wait, should we double-check this? Next up, something a little closer to home. Spreadsheets. Yes, Excel. The friendly green program that people either love, fear, or ignore completely. Turns out spreadsheets cause all kinds of problems when you don't check the formulas. In 2012, two economists, Reinhardt and Rogoff, published a study showing that when a country's debt-to-GDP ratio rises above 90%, economic growth drops sharply. It was a big deal. The paper was cited everywhere, used to justify economic policies, shared in political debates. But there was a problem. A graduate student tried to replicate their results, and couldn't. After digging deeper, he discovered that the Excel spreadsheet they used had an error, a simple one. A few rows had been left out of the formula. That's it, a few missing rows. A small mistake in a big spreadsheet that influenced international policy. See, you don't need rockets or satellites to break the world. Just a copy-paste error. Let's take a breath and look at something more recent. COVID-19. When the pandemic started, governments and health agencies relied heavily on mathematical models to predict how the virus would spread, how many people would be affected, and what kind of measures would help slow it down. Some models were helpful, some were way off, and while the models themselves weren't evil, they were based on the best data available at the time. They were also filled with unknowns, assumptions, estimates, and when your inputs aren't accurate, well, you already know what happens. Predictions fail, policies wobble, people get confused. To be clear, modelling is hard, especially during a pandemic. It's like trying to guess the weather while standing in a hurricane, but still, it's another reminder that math isn't magic. It's only as good as the information you give it. Now let's swing back a few decades. The British Trident submarine program. In the 1980s, the British Ministry of Defence developed new software to calculate missile trajectories for their submarines. The system worked beautifully, except for one thing. When they tested it in the Southern Hemisphere, it gave totally incorrect results. Why? The math had been written assuming Northern Hemisphere coordinates. The code didn't account for the fact that the Earth has two halves. Oops, millions spent. All because someone forgot that Australia exists. Speaking of forgetting things, let's talk about Mars again. No, not the orbiter this time. This time it's Beagle 2, a British spacecraft that was supposed to land on Mars in Everything looked good. It launched, it arrived, and then silence. No signal, no data. For years, nobody knew what had happened. Then in 2015, NASA's Mars Reconnaissance Orbiter found it, partially deployed, stuck on the surface. Turns out the lander's solar panels didn't fully open, which blocked the antenna. The math behind the deployment sequence hadn't accounted for a certain mechanical error. It almost worked. So close. But again, almost isn't enough in space. You either land, or you don't. And finally, let's go way, way back. Rome? A massive bridge collapsed during a military campaign. Historical documents suggest it was due to poor engineering and rushed construction, but modern analysis shows something more interesting. The arch supports were spaced too far apart. The materials couldn't handle the compression. The stress on each block was off by just a few degrees, which means even the Roman Empire, with all its glory, might have been brought down a little faster by a bad calculation. All of this tells us something important. We don't mess up math because we're bad at math. We mess it up because we rush. We assume. We overtrust the models or the formulas or the guy who said, "I'm pretty sure it's fine." And math doesn't argue. It just quietly follows instructions, right off the edge. So what can we do? Slow down, ask questions, build systems that double-check themselves, and, most importantly, stay humble. Because even a missing spreadsheet row can change global policy. Even a rounding error can crash a rocket. Even a misplaced minus sign can throw off a pandemic forecast. But every one of those mistakes, it's a chance to learn, to fix, to build better. Sometimes we talk about math like it's a villain. Cold, strict, full of rules. A system that punishes you for forgetting a decimal, or accidentally dividing by zero, or trusting a spreadsheet that hasn't had coffee yet. But tonight, let's step back. Let's turn down the volume, dim the lights, and look at something softer. Because beyond the numbers, the formulas, the calculations, there is beauty in math, even when it fails. Especially when it fails. Let's start somewhere unexpected. Nature. If you've ever looked at a sunflower, you've seen math. The seeds inside don't grow randomly. They spiral outward in perfect, elegant patterns, known as Fibonacci spirals. Each seed is placed at a specific angle, about 37.5 degrees from the previous one. This creates a tight, efficient packing, no wasted space, maximum sunlight, maximum beauty, all built from a simple sequence 1, that's Fibonacci. Each number is the sum of the two before it. Nature uses it like a secret recipe. Pine cones, pineapples, hurricanes, galaxies, all shaped by this quiet spiral. Why? Because it's efficient. Because it works. Because maybe the universe just likes pretty things. Then there's fractal geometry. You've probably seen fractals without even realizing it. Fern leaves, snowflakes, Romanesco broccoli, which looks like someone asked math to design a vegetable in its spare time. Fractals are shapes that repeat at different scales. Zoom in, and they look the same. Zoom out, still the same. Patterns within patterns within patterns. They're everywhere. Lightning, river networks, your lungs, the branches of a tree, even your brain. All of them shaped by recursive math equations that feed into themselves, like a mirror reflecting a mirror. Now let's go deeper. Play up. Just the sound of it is soft. P. It's one of the most famous numbers in the world. P shows up everywhere in circles, waves, pendulums, music and statistics. And yet, it never ends. 3.1475926535. It just keeps going. Forever. No pattern. No repeating. Just infinite, quiet chaos. Hidden inside something as simple as a circle. We've calculated pi to over 100 trillion digits, but we only ever really need about 40 of them. So why do we keep going? Because it's there. Because it's mysterious. Because there's something mesmerizing about a number that has no end, no rhythm, and yet still holds everything together. Even the places where math fails can be beautiful. Take imaginary numbers. Mathematicians invented them to solve equations that had no real answer, like the square root of a negative number. They weren't supposed to be useful. They were just weird, abstract ideas. And yet, today, imaginary numbers are used in electricity, quantum physics, signal processing, even MRI machines. Turns out these nonsense numbers help us describe the real world better than we ever expected, because math has a funny way of being useful, even when it looks ridiculous. And sometimes, just sometimes, the math doesn't quite work, but it still leaves something beautiful behind, like Gödel's incompleteness theorems. These are two of the most famous ideas in 20th century mathematics, and they basically say this: there are some things in math that can't be proven, even if they're true. Let that sink in. Even in a system built entirely from logic, there are limits, edges, unknowable truths. It's like discovering that even math has a soft spot, a place where certainty slips into mystery. And that's kind of comforting, isn't it? Even the most precise system we've ever built has a little wiggle room, a little poetry, because maybe math isn't just about being right, but maybe it's about exploration, curiosity, the joy of discovering something that's been hiding in plain sight. Like how the golden ratio, about 1.6118, appears in everything from seashells to the Parthenon to the Mona Lisa. Some of that may be coincidence, some may be overblown, but still, it's magical. And it makes you wonder, did the universe come with a blueprint? Or are we just finding patterns because we love to see them? Either way, math helps us look. It helps us ask better questions. It gives us tools to understand the chaos and find the quiet symmetry inside it. Even when we make mistakes, even when our models are wrong, even when we forget to convert pounds into newtons and send a spaceship into Martian oblivion, the math still has something to teach us. Not just how to calculate, but how to appreciate, how to notice, how to be in awe. So, the next time you look at a leaf or a spiral staircase, or a drop of water rippling across a still pond, remember, you're looking at math, not the textbook kind, the beautiful kind, the hidden kind, the kind that lives quietly in the background, whispering, I've been here all along. So, we followed this story from the beginning. A shiny spacecraft, carefully built by brilliant minds, launched into the stars only to disappear into the Martian sky because of a tiny math error, a unit mismatch, a silent misunderstanding, a pound instead of a newton, and with it $327 million, years of effort, and a big chunk of NASA's pride. But this isn't just a story about failure. This is a story about learning. Because if there's one thing NASA is good at, besides, rocket science, it's turning mistakes into progress. Let's take a closer look at what happened next. After the loss of the Mars Climate Orbiter, NASA didn't point fingers and sweep it under the Martian dust. They did what scientists do. They analysed it. Carefully, calmly, relentlessly. A formal review board was assembled. Dozens of pages were written. Engineers, programmers, managers, all interviewed. Every piece of software rechecked. Every communication traced. And what they found wasn't just a one-time mistake. It was a series of small oversights, stacked like dominoes. The software team used imperial units. The navigation team assumed metric. No one cross-checked the interface documentation. The systems didn't have automated unit validation. The teams didn't have formalized handoffs for key data. Everyone trusted that someone else had already double-checked the numbers. It was a communication failure wrapped inside a process failure, sprinkled with a dash of "but we've always done it this way." So, what did NASA do? They fixed it. They didn't just slap a warning label on the code or stick a sticky note on someone's desk that said, "use metric." They rebuilt the way teams work together. They introduced stricter interface control procedures. That means any time two systems talk to each other, whether it's software, hardware, or human teams, the expectations are spelled out clearly. Units must be defined. Data formats must be documented. Assumptions must be surfaced, questioned, and confirmed. In fact, after the incident, NASA made unit validation a required part of mission software testing. No more silent mismatches. If your system is expecting newtons and it suddenly receives pound for seconds, it doesn't just smile and crash. Now it waves a flag, sends an alert, says, "Hey, this doesn't feel right," because that's what systems should do. Not just function, but protect. Protect the mission from tiny human oversights. Protect brilliant ideas from vanishing into space because someone forgot to add a line of documentation. NASA also began encouraging more cross-disciplinary reviews. That means engineers from different departments are now expected to sit in the same room, walk through mission-critical processes, and say things like, "Wait, what unit is this?" And instead of being met with blank stares or ego-driven eye rolls, the answer is now part of the process. It's normal. It's expected. Because asking questions doesn't slow down a mission. It saves it. And the best part? These lessons didn't stay inside NASA. They were shared openly with the global engineering community. Because mistakes like this one aren't just NASA problems, they're human problems. And if we can learn from one organization's failure, maybe we can prevent 20 more down the road. And that's what makes this story kind of beautiful. It didn't end in disaster. It ended in growth. Because when you send machines to space, you also send pieces of yourself, your ideas, your logic, your systems, and sometimes your blind spots. But each mistake is a mirror, and what you do after the mistake. That's the real mission. So what came next? NASA kept going. They sent the Mars Odyssey. It worked. Then the Spirit and Opportunity rovers. They worked. Then Curiosity. Then Perseverance. Then Ingenuity. A tiny helicopter flying through the thin Martian air. All successful. All built on systems that were stronger, clearer, and more robust. Because of a mistake made decades earlier. That's how science works. Not in a straight line, but in loops. Test. Fail. Learn. Adapt. Try again. It's not glamorous, but it's powerful. It's what makes engineering resilient. It's what makes exploration possible. And here's a quiet thought. That $320 million spacecraft. It still taught us something. It showed us what not to do. It revealed the cracks in a system before those cracks got even bigger. And maybe, just maybe, that's worth the cost. Because what's more expensive than a failed mission? A repeated failed mission. NASA made sure that wouldn't happen. So the next time you hear someone joke about the orbiter, oh yeah, the one that got lost in space because someone forgot the units, you can smile and say, yes. And because of that, we got better. We made the system smarter. We made the engineers safer. And we made the future just a little more precise. We've seen what happens when the math goes wrong. A tiny unit mismatch. A silent assumption. A spacecraft lost forever. But now, let's talk about what happens when the math goes right. Because after the Mars Climate Orbiter incident, NASA didn't quit. They didn't say, well, Mars is too hard. Let's just focus on Earth stuff. Maybe build a better microwave. No. They did what space agencies do best. They recalculated, rebuilt, and launched again with better math, stronger systems, and a deeper respect for every decimal. So tonight, let's float gently through the missions that followed, the ones where the math worked, the ones that made history quietly, beautifully, and properly this. First up, Mars Odyssey, launched in 2001. Just 2 years after the orbiter failure, a spacecraft designed to study Mars from orbit, and also act as a relay for future missions. This time, the unit conversions were double-checked. The software interfaces were standardized. The navigation math, flawless. Odyssey entered orbit perfectly. It's still operating today, over 20 years later. That's what happens when you respect the math. Next came something special. Spirit and Opportunity, twin rovers, identical siblings, launched a few weeks apart in their job, land on Mars, drive around and explore the surface for 90 days. That's it. Just 90 souls, Martian days. But here's what actually happened. Spirit lasted for over 6 years. Opportunity? She kept going for almost 15 years. Why? Because the engineering was solid. Because the math behind the trajectory, the entry, the descent, the landing, all of it was done with surgical precision. They knew exactly how fast to fall, exactly how to inflate the airbags, and exactly when to bounce across the Martian surface like an interplanetary beach ball. Not only did the math work, it danced. The rovers became legends. They climbed hills, took selfies, found evidence of ancient water. One of them even got stuck in sand, like a toddler at the beach, and NASA tried for weeks to free it, just because they loved it that much. And the data? Priceless. All thanks to math that wasn't rushed, or assumed, or whispered between teams in different units. It was checked, validated, agreed upon. Then came the Curiosity rover. This one was big, heavier, smarter, full of instruments. So heavy, in fact, that the old bounce landing technique wouldn't work anymore. NASA needed something new. So they invented a sky crane. Yes, a literal flying robot platform that hovers above the Martian surface, lowers the rover on cables, then flies away to crash safely somewhere else. It sounds insane, but the math made it possible. Orbital mechanics, descent trajectories, thrust calculations, cable tension. Everything had to be perfect. And it was. In 2012, Curiosity landed safely in Gale Crater and immediately got to work, drilling into rocks, sampling soil, and proving that Mars once had conditions that could have supported life. All because someone said, "What if we land it with a space crane?" And the math replied, "Yeah, okay, I can make that work." But we weren't done. Next came Perseverance, launched in 2020. Landed in This rover is the most advanced one yet. It's searching for signs of ancient microbial life, collecting samples, taking videos, running experiments. But the real show stealer? Ingenuity. A tiny helicopter. The first aircraft to fly on another planet. Think about that for a moment. Mars has thin air, about 1% of Earth's atmospheric pressure. Flying a helicopter there is like trying to hover a drone at 100,000 feet above Earth. The rotor blades had to be extra long. The motor had to be light but powerful. The math behind the flight, unforgiving. Lift, drag, gravity, Martian wind. But guess what? It worked. Ingenuity flew. Then flew again. And again. Over 70 flights at last count. We built a drone that flew on a different planet. That's not just engineering. That's poetry. Written in equation. And all of it, every second of it, is what happens when we learn from our mistakes. The climate orbiter taught us humility. These missions, they taught us hope that we can land on Mars, that we can fly on Mars, that we can build math strong enough to carry our questions across millions of kilometers of space, land them gently on red dust and start listening for answers. There's something beautifully quiet about it all, because we don't often think of math as emotional, but it kind of is. Every number on those mission plans, it's a promise. Every calculation, a leap of faith. A spacecraft can't improvise. It can't guess. It just follows the math. So when you see a rover crawling across a distant planet, snapping photos, drilling into rock, sending back data, you're watching math made real, made durable, made curious, made alive in a sense. And it's not perfect. Sometimes the wheels get stuck. Sometimes the dust covers the solar panels. Sometimes the helicopter lands a little crooked. But we get better every time, because now we ask the right questions. What unit are we using? What assumptions are we making? Who needs to be in this conversation? And that shift from trust the system to build a better one is what will carry us even farther, to Jupiter's moons, to Saturn's rings, to exoplanets so far away the light hasn't even finished its journey yet, because we've learned, we've evolved, and we've built a language, a quiet, powerful language that can carry us there. A language made of numbers. We've come a long way, from the loss of a spacecraft to the quiet triumph of little robots rolling across another planet, from missed conversions to drones flying through Martian air, from human error to mathematical elegance. But there's still one last idea to explore tonight. It's tiny, almost invisible. It hides behind a dot. It looks like nothing, but this thing can change everything. A single decimal, just one. One tiny dot, one extra zero, or one missing one. The kind of thing your eyes skip over. The kind of thing you type without thinking. The kind of thing that doesn't feel important until it is. Let's start simple. If I told you the difference between 1.5 and 1.05 was only 0.45, you'd shrug. It doesn't sound like much. But what if that's 1.5 meters versus 1.05 meters in a blueprint? Now your wall is almost half a meter too short. What if it's 1.5 liters of medicine versus 1.0? That decimal becomes a medical emergency. And in space, decimals decide everything. How fast you're falling, how far you'll land, how long your thrusters should fire. There is no wiggle room. Decimal errors have crashed rockets, misaligned satellites, sent spacecraft sailing into nothingness, and yet we still underestimate them because they're small, because they're quiet, because we think precision is for robots and test scores and obsessive personalities. But here's the truth. The world runs on decimals. Your bank account, decimals. Your blood pressure, decimals. The amount of oxygen in your scuba tank, the dose of anesthesia before a surgery, the fuel mix in a jet engine, every one of those depends on the exact position of a tiny floating point. Move it, and the system changes. Sometimes a little, sometimes catastrophically. Even the stock market has been rocked by decimal errors. A single misplaced zero in a trade order has triggered billion-dollar swings. Stocks bought at 100 instead of 10 or sold for 1.0 instead of 1. Decimal mistakes don't feel like mistakes until the damage is done. And yet, decimals also give us power. They let us measure things precisely. They let us refine our answers. They help us improve, adjust, and optimize one subtle step at a time. The difference between a 0.99, not much to the eye, but in math, one is almost full, and the other is. It's the line between not quite and just right. Decimals live in the space between certainty and curiosity. They give us room to ask better questions. To say, I don't just want to know the answer. I want to know how close I am, and how much closer I could get. That's what makes them magical. Because behind every decimal is a story, a decision, a moment of precision in a world that loves to rush. You don't need to be a rocket scientist to appreciate that. You just have to pause, to notice, to care enough to place the dot where it belongs. Because sometimes, a small correction in the right place can save the mission. And that's not just a space thing, that's a life thing. Think about the way we speak to each other. Sometimes a single word, a soft correction, a pause, a "you're right" instead of "actually" makes all the difference. In relationships, in teams, in how we navigate the world, precision isn't just mathematical, it's emotional. It's about being intentional, and that's what makes decimals feel kind of human. They remind us that big things depend on small things, that attention matters, that taking an extra moment to check the number or reread the message or ask the question might be the thing that changes the outcome. The decimal isn't loud, it doesn't wave its hands, but it's always there, waiting quietly for us to get it right, or get it wrong, and both paths have consequences. So the next time someone tells you that math is boring, you can smile, because you know something they don't. You know that a single dot, a quiet decimal, floating in the middle of a number, once destroyed a spacecraft, and you also know that same precision helped us land 6 more safely. A decimal can end a mission, or launch one. It can cost millions, or save lives. It can break things, or fix them. It's not about the number. It's about the care behind it. And if that's not poetic, I don't know what is. In our final chapter, we'll end where we began, with a spacecraft drifting through the silence, numbers softly whispering into the void, and a quiet invitation to sleep well and double-check your units. But for now, rest, let the decimals line up, let the numbers find their place, and let your thoughts float calmly through the space between precision and peace. Imagine this: a spacecraft, silent, sleek, the size of a piano, drifts alone through the dusty pink sky above Mars. Its antenna is still pointed home, its sensors still reaching for signals. But there's nothing, because somewhere, far behind it, a number was wrong, a force miscalculated, a unit misunderstood, and now it's falling. Not fast, not yet. It glides through the upper edge of the Martian atmosphere like a leaf floating through evening wind. No sound, no panic, just drifting, falling in the most mathematical way possible. An arc, a curve, a quiet calculation being resolved in real time. At the other end of the signal on Earth, engineers wait, staring at blinking screens, watching for telemetry, but there is none. They send a signal. The spacecraft does not reply. They send another. Still nothing. The curve has gone too low. The atmosphere is too dense. The math was off. Just a little, but just enough. There's no explosion, no debris, just silence. The kind of silence that feels heavy. The kind of silence that carries numbers. And somewhere inside that spacecraft, in its processors, its memory banks, its carefully coded flight software, the numbers continue to run. The systems don't know they've failed. They're still solving equations, still calculating orientation, still attempting to transmit according to their programming. Somewhere inside that metal body, a tiny clock ticks onward. T-minus nothing. Even in failure, the math continues, because that's what math does. It doesn't know triumph. It doesn't know shame. It just follows the rules. So picture it, the Mars Climate Orbiter gliding silently through thinner and thinner air, its heat shield starting to glow, its thrusters still prepared to adjust trajectory, its instruments still ready to measure Martian weather, that it will never see, like a music box playing the final notes of a song no one hears. You can almost feel it, the soft hum of circuits, the tiny whir of gyroscopes spinning against gravity, a machine trying its best to fulfill its purpose, even as it fades. And isn't there something beautiful in that? Something honest? A spacecraft, still solving for X, even as the atmosphere embraces it, even as it melts, even as the mission ends. Back on Earth, the engineers exhale, not in anger, not in panic, just quietly, because they know. They know what happened, and they know what they'll do next. They'll learn. They'll fix the system. They'll improve the math, because that's what humans do. We build things. We lose them. We ask why. And then we try again. But for now, the spacecraft drifts. The arc is smooth. Perfect even. Because the laws of motion don't care whether the input was correct. They just do their job. And the numbers, quietly, obey. So as you drift off tonight, picture it. This small machine, somewhere above Mars, falling with grace. A silent poem written in velocity. A lullaby composed in kilograms, meters per second, and regret. There is no judgment, no blame, just numbers falling. And in a strange way, it's peaceful, because even failure has its elegance. Even broken machines can glide beautifully. Before they fade, even lost things follow the rules of the universe. And in that, there is comfort. So let your thoughts go quiet now. Let the formulas soften. Let the trajectory settle into your dreams. The spacecraft has stopped reporting, but the story continues. In every mission after, in every equation double-checked, in every lesson carried forward, the silence wasn't the end. It was a new beginning. And the numbers, they'll be waiting, not just of the story, and now we've reached the end, but of the quiet journey we've taken tonight together. One decimal, one mistake, one perfectly placed equation at a time. A beautiful machine, built by brilliant minds. We followed its path across millions of kilometers. We started with a spacecraft. We watched it vanish. How could one tiny math error, one invisible misunderstanding erase something so big? And we asked, how? And the answer was simple. Even the smallest ones. Because numbers matter, especially the smallest ones. It was about how math runs the world. But this was never just about a missing unit. Not loudly, not dramatically, but softly, silently, like gravity, like oxygen. We saw it in the people who built the spacecraft, like a gentle pulse behind everything we touch, in the engineers who forgot to check the units, in the systems that assumed too much, in the scientists who asked questions too late. But also we saw it in the people who learned, who owned the mistake, who rewrote the rules, who made the next mission better. Not the crash, but the correction. That's the real story. We talked about imperial and metric, not the silence, but the promise that came after. We talked about fractions and GPS and grocery store math. We talked about medical dosages and algorithmic romance. We even talked about broccoli. Why? Because math is everywhere. It hides in the quietest corners of your life, in the way your phone works, in the way your heart beats, in the way your cat lands perfectly on your keyboard every time you're working. And maybe, just maybe, that's what makes it beautiful. Not the complexity, not the symbols, but the fact that it's always there, waiting, measuring, helping, guiding, letting us build cathedrals and launch satellites and bake cupcakes without burning them. You don't have to be a math genius to appreciate that. You don't have to solve equations in your sleep. You just have to notice, to say, hey, that's cool, that's clever, that's kind of beautiful, not as something scary, and then maybe you'll start to see math the way I do. Not as something hard, a guide, but as a friend. This fits here, that connects there. Keep going, a gentle, persistent whisper in the background of the universe, softly saying, because here's the secret. It doesn't care if you never learned what a logarithm is. It doesn't care if you got a C- in algebra. Math doesn't judge. It doesn't care if you forgot to carry the 1 or wrote the number upside down. Still whispering. It's still here. Still holding the world together. One ratio, one angle, one lovely irrational number at a time. So tonight, let's say goodnight to the numbers. Not goodbye, just goodnight to the formulas who hold bridges in place while we walk across. To the decimals who quietly shift reality by tiny amounts. To the algorithms who send us raccoon videos when we feel sad. To the engineers who launch rockets. To the equations we got wrong, and the ones we'll get right next time. To the sleepy minds who drift off listening to stories about space and numbers and soft accidental chaos. To the students struggling with fractions. To the poets who write odes to pi. Because every person who's ever counted on their fingers, this is your story too. Who's ever wondered, does this number matter? Who's ever tried to figure out a tip at dinner and guessed, you are a mathematician, whether you feel like one or not, is part of this, to measure meaning. Because to be human is to notice patterns, to dream in diagrams and count the stars. And that makes you part of something beautiful. So, let the numbers rest now. Let the calculations pause. You've done enough for one night. Let the graphs fade softly to 0. Let your brain unplug from the spreadsheets and the conversions and the long-forgotten high school equations. Let math carry you instead. You've carried it long enough. And if you ever find yourself doubting, just remember, even when the decimal's in the wrong place, even when the math breaks your heart, even when a spacecraft fails, it still gives you one more chance to learn, to improve, to try again. And that's the most human equation of all. So sleep well, my friend. You've just travelled through space, through logic, through error, through elegance. And now it's time to return home. Good night, little numbers. Good night, math. Good night to you.